Allora vi ringrazio per la partecipazione e direi che do la parola a Dimitri Breda per introdurre la relatrice.
Grazie Andrea, buonasera a tutti. Io passo all'inglese come consuetudine. So it is a true pleasure to introduce Francesca Scarabel, our speaker today. And Francesca left the University of Udine in 2014 with a degree in mathematics and then got her PhD at the University of Helsinki under the supervision of Mats Gillenberg, Odo Dickman, and Rosanna Vermiglio. And after visiting Szeged in 2019 and 2 years postdoc at York University in Canada, she is now a research associate at the University of Manchester. Francesca's initial focus on numerical methods for studying the dynamics of structured population models has now fruitfully expanded in terms of modeling and applications to epidemiology, with several contributions also to the study of COVID-19. Recently, she has been working on modeling contact tracing, another strategic aspect in contrasting the current pandemic and the topic of today's talk. So welcome, Francesca, and thank you very much for contributing to the series. Please.
Thank you, Dimitri. Thank you, Andrea. It's a real pleasure for me to be here, to be invited to this seminar series. Sorry, let me. So, yeah, I am now, as Dimitri said, I'm now a research associate at the University of Manchester, but I've conducted this work mainly when I was doing my postdoc in Toronto at York University. I also want to mention my my continuous collaboration with the University of Udine, which is my where I'm really connected to. This presentation comes from work that has just been published. It has come out yesterday in the Royal Society Open Science, and I've conducted this research with my supervisor in York University, Professor Jianong Wu, Lorenzo Pellis, who is a researcher here at the University of Manchester, and Nicholas Ogden, who is section director at the Public Health Agency of Canada. As I mentioned, during the project, I was funded by Canadian funds, and I'm currently I have a contract within the Juniper Consortium in the UK, which brings together 7 universities in the UK. Before I start with the proper talk, I want to mention briefly what I'm going to talk about, which is contact tracing, and probably we have all heard about contact tracing during this year of COVID-19. This is the process of identifying and isolating individuals among the contacts of one confirmed case. And the goal of contact tracing is to stop as many infection chains as possible, as early as possible. So the advantage is that it is a measure that is tailored to people that are known to, that have been exposed to the infection, and is not a mass intervention. And there are several strategies in public health. One strategy is forward tracing. So once one infected individual is detected, the search is for the secondary infections. So who have been infected by this one case. This is in contrast with what backward tracing, where the search is for the who infected the index case. And then by full tracing, we mean a strategy that combines both. So one goes and search for the infector of the index case and then forward again to find the secondary cases. This I mentioned for context. I will focus on forward tracing here. So just the search of the secondary infections. And why I started talking about contact tracing is because I want to mention what are the main challenges in modeling contact tracing. So a mathematical model of contact tracing should account for several different things. Of course, the underlying infection spread, and then some diagnosis or screening program that can initiate contact tracing, like for example, testing or preventive screening if we are thinking at sexually transmitted disease. And we should take into account all the contacts between individuals and the possible infection transmission due to this contact. And here is the main difficulty of modeling contact tracing, because contacts are distributed in the past compared to the one individual that has been detected now. And those contacts who possibly have been infected, they have already progressed through some disease stages. So they may be already infectious or not infectious yet, or already recovered yet, and possibly have generated new infections. So this is very complicated to capture. And therefore, most studies use stochastic approaches, in particular agent-based models, for example, or branching processes, network models, or some sort of mean field approximation to network models. Here I want to mention that stochastic approaches like agent-based model are really, really powerful, because they allow to take into account many heterogeneities in the system, both in the contact process or in the spatial process or maybe demographic process. But because they mainly explore the result via simulations, and they often hide the relations between parameters and output of the models. So with stochastic agent-based model, it's quite difficult to understand some general results or general relations. I want to mention this because to stress the importance of deterministic models, which are maybe less powerful in incorporating some of the heterogeneities of the system, but have the advantage that are usually faster to simulate and have the possibility to investigate some analytical relations between parameters and some general structures in the models and in the results. So the most common deterministic models are ODE compartmental models, which are normally the hammer with which we tackle problems. And probably many of us have worked with compartmental ODE models, especially in addressing the practical problems in this pandemic, the urgent problems. But in the case of contact tracing, compartmental ODE models are difficult to use because they fail to capture the details of the distribution of contacts in the past, or this is very difficult to capture rigorously in an ODE model. And here I was very lucky during this year, because while we were working with very pragmatic and practical question for public health in Toronto, with my supervisor, I was lucky enough that my supervisor loves both pragmatic and public health questions, but also more theoretical aspects and more theoretical and mathematical aspects. So while we were doing some very, very applied work, he also proposed to me a more theoretical question, which was how one can construct a deterministic model of contact tracing that really captures the main essence and the main features of contact tracing. And his intuition was that because when one individual is detected, we should look at the infectees and then at the infector. His intuition was that there should be some delayed and advanced arguments, time arguments in the model, because we are looking both at the future and at the past. So that's what motivated then my research. So what I want to present here is especially the modeling approach we have taken, which is based on structured population models, and it really goes from the individual level parameters and lift them up to the population level parameters in a mechanistic approach. So I somehow want to have a break from very pragmatic aspects of the pandemic we have seen this year, and have a break into a more theoretical framework. But on the other hand, so if someone considers this a bit too theoretical, I will also show some applications to the case of COVID that really show that although this method, this approach might seem theoretical, is also quite useful in practice, or quite flexible to capture some of the important features of contact tracing. In particular, I will show some how one can use the model to investigate the contribution of diagnosis contact tracing to control the infection. And this may be a bit, this may sound a bit, well, not front edge research, because now the current research focuses more on vaccination now that we finally have some vaccines. But still, contact tracing will probably still keep a primary role, because we all know that variants come in all the time, and also there are some open questions like we are all wondering if the summer will be as good as last year, and if this is a matter of seasonality or of, for example, low prevalence last summer that allowed for very intense and effective contact tracing. So this is a topic that will probably not become outdated. So we'll first start with the presenting the model, and I'll probably not be able to keep an eye on the chat. So if there are questions, feel free to just speak up and ask the questions. So the model I'm going to present is starts with a very standard structure where the population is divided into 3 classes, like susceptibles, infected, and removed. Susceptibles are the individuals who can contract the infection. Infected individuals can pass the infection to others, and removed individuals are those who are permanently immune and do not infect others. And the main assumption is homogeneous mixing between individuals, and the fact that individuals are identical and independent of each other for what concerns epidemiological properties. And as I mentioned, there are 3 main processes involved: the standard infection process, the process of diagnosis from symptoms, so a process that is independent of what's happening in the to others, but it's just a detection because one single individual develops symptoms, go to the hospital, for example, and get tested and get diagnosed and isolated, or possible contact tracing. And as I mentioned, the modeling approach I'm using is starts from the individual level and then lifts the parameters to the population level. So we look at one single individual and define parameters for this specific individual, infected individual, in terms of the time that has passed since the infection. So if this is an infectious individual, and I call tau the time since infection, or age since infection, there is no demographic age in the model. So whenever I mention age, I mean age since the infection. I can attribute some parameters to this individual, like its infectivity, the incubation period, which is the time to onset of symptoms, or a rate with which this individual is diagnosed from symptoms, or a rate at which the individual is traced in time. And then using this parameter at the individual level, I want to describe the 3 main processes of the system. The first one is the infection process. And we assume that infection happens upon contact of a susceptible individual with an infected individual with a certain probability. That is described by the individual infectiousness, which I call beta. And this function accounts both for the number of contacts made by the infected individual and the probability of transmission. So if I look at one single infected individual and I count how many new infections this individual generates, I can simply multiply this infectiousness times the probability that the contacts are actually susceptible. So this is the fraction of susceptible individuals over the total population. So now I have described how many new infections one single individual generates. I can also count at the population level how many new infections are there at time t. This is called the incidence of the infection. I call it y. And this is simply given by integrating over all the possible ages since infections, tau, the number of new individuals that each individual makes, new infections, and times how many individuals of this age since infection are there in the population. And if we first assume that individuals are never isolated and they go around and spread the infection normally, the number of individuals that have age tau now is equal to the number of individuals who got infected exactly at time t minus tau. So the incidence at time t minus tau also describes the number of individuals that have age tau now. So this takes care of the infection process. And now I want to describe the assumptions on the diagnosis process. This process is assumed to be known because this is either determined by the epidemiological parameters of an individual, for example, the incubation time, so the time to develop symptoms, and the test positivity, so the probability that a test becomes positive or negative. And it is also determined by the screening policy, the public health policy. For example, if the policy is to test all symptomatic individuals only, or random testing, or some other kind of type of policy. But we can assume that this is prescribed and known. And we assume that is prescribed by assuming a certain rate at which a single individual gets diagnosed at age tau. And this also determines the probability that an individual has not been diagnosed before a certain age. So age with a subscript d will represent the rate, and the calligraphic F will determine the probability of not being diagnosed, which I also call survival probability to symptoms. And this is can be obtained explicitly from the rate. Now, I also assume that the diagnosis process is independent of time, although this may not be true in practice, as we saw that with COVID, the testing policy have changed a lot during the year. And I will assume that individuals are perfectly isolated after diagnosis. So after their diagnosis, they cannot infect anyone else. This is also kind of a strong assumption. The final process we need to describe is the contact tracing process. And this is much more tricky because the probability that an individual is traced depends on the underlying epidemic. It depends if the infector was detected, in this case, in forward contact tracing. So this may be time dependent, and I would not be able to prescribe it a priori, so we take it as a known. And when I say I take it as a known, I mean that I will define a variable, which is the rate at which a single individual is traced. This variable I call h with subscript c, and now it is unknown, and it is also time dependent. This is different from the diagnosis process. And to this rate, I can also associate a probability of not being traced before a certain time, which is also given by the integral, by the negative exponential of the integral of the rate. Although I should mention that now, because the rate has two variables, has the chronological time and the age since infection, now this integral is performed along the characteristic lines. But still, the survival probability to contact tracing is completely determined by the rate. Now, as I mentioned, I restrict to forward contact tracing. So again, when an index individual is detected, the policy is to search for their secondary cases, so for the people who he or she has infected. And then I also assume that after tracing, individuals are perfectly isolated, so they don't contribute to the infections. And to present the model, I also assume that there's no tracing delay, so contacts are immediately traced. And I also assume, for simplicity, that tracing is iterative. So contacts of contacts of contacts are immediately traced. And this makes the model a bit abstract. But I believe it is a minor effect. And it is useful to illustrate the model and the method first. Now, I will use also a parameter epsilon with subscript c, which represents the fraction of the secondary contacts that are effectively traced, because some may be missed by in the process. Now, this is a sketch of the process I'm going to model. Now, if I look at an initially infected case, this gray case here, and I represent with red crosses the infection events. So every red crosses, from every red crosses, a new infection starts, and those progress in time. Then the idea is that this one individual can be diagnosed at some point in time because it develops symptoms and gets to the hospital and get diagnosed. When this individual is diagnosed, then contact tracing finds searches first for all the contacts. So this two individuals, 2 and 3, and also because we assume iterative tracing, we also search for the secondary cases of these 2 cases. So also for the orange cases that were generated by individual 3. If contact tracing finds this individual, they are isolated and they don't contribute to the infection anymore. But some of them may be missed, and if they are missed, they still remain infectious and go on producing new infections. So this is a scheme of what I will have in mind when I construct the system. And to construct the system, I first look at an equation for the incidence, so to describe the behavior of the infection in the population. Yeah, we had previously our integral equation describing the incidence in the absence of isolation. But if now we have diagnosis and tracing, the individuals who were infected at time t minus tau could have been isolated in the meantime. So we need to multiply this factor by the probability that they have not been isolated yet by time tau. And this calligraphic F contains the probability that they are not being diagnosed and not being contact traced before time tau. This is simply given by the product of the 2 probabilities of not being diagnosed and not being contact traced. And the reason is that because we assume that individuals are independent of each other in terms of epidemiological parameters. The fact that an individual is diagnosed is at some time is completely independent whether it's the infector or whether the infectee have been diagnosed themselves. So somehow the event of being diagnosed or being contact traced are independent for one single individual. So this is a renewal equation for the incidence Y, and this is pretty standard in epidemiological models. And also, so I want to mention that the susceptible individuals can be written explicitly in terms of the incidence, because we know that they satisfy this differential equation that can be solved explicitly in terms of the total initial population and past information on the incidence. So the susceptible individuals can be expressed in terms of the incidence. The only thing here that is not known is this probability calligraphic F, because it depends on the contact tracing process F with subscript C, which is unknown in the system. So we need to find an equation for the contact tracing process. And here is the clue observation for describing the contact tracing process, is that the probability that an individual is traced at a certain time is proportional to the probability that the infector is detected at the same time, because we assume no delay. So we need to put these two probabilities in relation. And if I look at the probability that the infector is detected, so an infector is detected if it is either diagnosed or traced at the time. So here we observe in Word what will become, what will give our final equation that links the probability that an individual is traced at a certain time with the probability that its infector is traced at a certain time. So we will have an equation for the tracing probability. And because all of our parameters are determined by the age since infection of individuals, we really want to break down this probability by conditioning on the age of infection of the infector. So in this graph, the blue line represents the infector. The infection event happens at time t minus tau, and the orange individual is the secondary case. And at time t, we have that the secondary case, which is our index case in the model, has age since infection tau, and its infector age since infection s plus tau. So we want to put in relation the probability that the index case is traced at time t with the probability that the infector is either diagnosed or traced at time t. So I go to the equations, and the probability that an individual is traced at time t is given by the rate times the differential dt. So this is what we will have on the left-hand side. This is what represents this probability here. And as I said, this is proportional with some constant representing the fraction of secondary contacts that are effectively traced. This is proportional to the probability that the infector is detected. And here, we want to break down the probability conditioning on the age since infection of the infector. So here we multiply the probability that the infector has a certain age times the probability that such infector has been detected exactly at time t. While we know also, the other information we know is that this one infector was not detected before time t minus tau, because that's the point when we know that the infection happened. And if I translate this in formulas, I call psi here, consider it as a definition. This is the probability that the infector has the age since infection s at the infection time. But this part here simply represents the fact that the infector was detected exactly at time t. This is described by the sum of the rates here. And then, but then we know that it should not, so it hasn't been detected before. So here we have the survival probability. So this is what will give us an equation for the variable h with subscript c, representing the tracing rate. And if I focus on the probability psi, I don't want to stop on this slide because this is actually, so for time reasons, because this is actually easy to calculate. But the idea is that the probability that an infector has a certain age can be computed, can be expressed explicitly in terms of how many individuals, infected individuals are there around in the population. So can be expressed in terms of the incidence and in terms of the probability of not being isolated yet. So this can be made explicit. And then, okay, and this is the final model. So this is the last kind of abstract mathematical slide. The idea is that this is our system of equation that is closed, and this is formed by two equations, one for the contact tracing rate and one for the incidence. They're both integral equations. And the system is closed because we can express the survival probability calligraphic F in terms of the rate of this variable here. And we have an explicit expression for the susceptible individuals. So this system is closed. And the renewal equation for the incidence is pretty standard. And this is delayed in time because the integral goes back over the history of the incidence. And we observe delayed argument also in the first equation. But what is also interesting is that we also have advanced arguments in the age since infection, because the variable defined at the age since infection tau depends on future values of the age since infection. We observe it here and also here. And intuitively, this can be explained because if I look at an individual with a certain age since infection, and I look at the infector is always older. So the age since infection is always higher. And the other, so after all, this model represents a quite complex model, but it fits into a slide. And the other advantage is that it can be solved using numerical methods, simply using quadrature rules to approximate the integrals. So we were able to solve it explicitly. Also, just to stress the point that this system is less abstract than it seems. So the fact is, I am very aware that the contact tracing rate is a very abstract quantity. This is hardly measurable in practice, and it's of no use, basically. But using this rate, we can compute all or most of the concrete quantities that are of interest in practice. For example, the number of individuals that are diagnosed at a certain time, or the number of individuals that are traced at a certain time. These are just given by some integrals over the variables we have. And these integrals can, again, are easy to approximate numerically. So although the system is given in terms of something that is really abstract, it is quite handy to use. Another advantage that I mentioned about deterministic models is that they allow for analytic expression of important quantities. So if we look at the reproduction numbers, now we are in the context of an emerging epidemic, so where we assume that the population is completely susceptible. And we look at the reproduction numbers that describe the average number of secondary infections produced by one infected individual. Then we can write those reproduction numbers explicitly. And in particular, we can define three types of reproduction numbers. The standard reproduction number R naught, which describes is the reproduction number when there's no public health measure in place. We can define a reproduction number RD when there's only diagnosis in place in the population, and the reproduction number when both diagnosis and tracing are have an effect. And we have explicit formulas for this. Having explicit formulas allows to compute these quantities quite easily and also to extract general insights. So having these formulas, it's really easy to prove that the epidemic is under control if the fraction of transmission that we are able to, that occur before isolation, so that we cannot prevent, is less than 1/R0. And this is regardless of how isolation is achieved, either by tracing or diagnosis. Okay, so this was the modeling part. Now I want to conclude with some applications to COVID-19 to to show that the model can actually be applied for making some concrete analysis. And in particular, we have investigated the impact of the diagnosis coverage, so how many individuals are actually identified just from symptoms, and the delay at which this happens, the tracing coverage, so how many contacts are effectively traced, and the tracing window, by which I mean how many days back from detection of a case we trace individuals. Is it 2, 3, or 4 days? And then we also investigated what happens just qualitatively, what can happen when contact tracing is interrupted for a certain period of time under limited resources. And to represent COVID-19, I took parameters from the literature. In particular, what I need is the infectiousness beta, which I have taken from some estimates of the generation time distribution, and the diagnosis rate, for which I've simply taken some estimates for the incubation time, and then shifted this incubation time by 1, 2, or 3 days, representing the time necessary from symptoms to obtaining a positive test and then being isolated. And the first very easy analysis one can make is about what parameters allow control. Here I have investigated the parameters related to diagnosis, so how many individuals are effectively diagnosed and with how much delay. In the case of relatively high reproduction number, this is still low, considering the estimates of the unconstrained reproduction number for COVID, but this plot is already indicative of the difficulty of controlling COVID, because the lines in the plot represent, so distinguish the region where the disease is controlled, the epidemic is controlled. The epidemic is controlled below these lines, and each line represents a different contact tracing strategy. So the orange line represents a perfect contact tracing where all contacts of detected individuals are isolated. And then down to the blue line, which is not even visible in the picture. The blue line would represent a strategy where there is no contact tracing in place at all. And from this graph, we already observed that only extremely high, almost perfect diagnosis, like of almost all individuals in very, very short time, would allow control for very high value of contact tracing coverage. So this describes how difficult would be to control the epidemic without a good contact tracing strategy in place. This is not probably a new result, but this is very immediate to obtain from having analytical formula at hand. And then compared to this graph, we observed that when the reproduction number, the basic reproduction number is lower, so describing a situation where there is some physical distancing already in place, the controllability region becomes much, much larger. Then another thing that was very easy to investigate was the effect of tracing coverage and the tracing window. So basically the public health effort in contact tracing in reducing the effective reproduction number. So on the y-axis is the effective reproduction number with both diagnosis and contact tracing. And we can see that increasing, so if we manage to increase the tracing coverage, we can get the reproduction number down, or also tracing contacts for a larger time window. So 2 days, 3 days, or 4 days brings this line back and down. And we also observed that the most difference is if we trace 2 versus 3 days back in time. Then when we get to 4 or 5 days, it's not as relevant. This is due to the shape of the infectiousness profile. This is a mostly qualitative picture. I have plotted the solutions corresponding to this previous analysis. These are obtained in an epidemic where all the population is susceptible. So actually the system is linear, and we can have the explicit solution for the contact tracing rate. So on the left, I've plotted the solution from the system, the numerical solution. And on the right, I have plotted the full detection rate. So the sum of the diagnosis rate, which is the basic line that starts gray and then goes purple, plus the contact tracing rate. This is just to illustrate, to make it visible, what is the effect and the advantage of contact tracing is to really identify individual early on in their infectious period, or early on in their infection, I should say, much earlier than the diagnosis. I must say this this very high values for very low agents infection are due also to the fact that this is a kind of optimistic scenario where contact tracing has no delay, so it's quite effective. This is unlikely to be as good when we include delays in the contact tracing rates, but it's still qualitatively interesting. And this is a qualitative, again, example. Here we wanted to show how important is the relation between prevalence of the disease and contact tracing efforts to control the disease. We have simulated some epidemic. So in blue, on the left panels is the incidence, so the new cases in time. And then in red and yellow are respectively the diagnosed and traced individuals. And this is an example, the first line is an example where the epidemic is actually controlled. It is declining when diagnosis and contact tracing are in place. Then we imagine that for some reason, contact tracing is lifted because, for example, the efforts is shifted to some other region. So contact tracing is interrupted, no individuals are traced anymore, and the epidemic starts growing again. And then when contact tracing is introduced again, the epidemic is controlled again. Cases go down. This is visible also in the estimated growth rate. On the right, I have the numerically computed growth rate, which is negative before the interruption. It jumps to positive during the interruption, and then at the same value, negative again after the introduction of contact tracing. But then the picture is very much different if the interruption of contact tracing is longer. This is visible in the bottom panels. Here we have an additional assumption, which maybe I didn't mention clearly yet. The additional assumption is that we have some maximal capacity to testing, or sorry, to tracing. So we cannot trace. So when this capacity is hit, then the tracing efficacy is reduced. And then in this case, if the interruption is longer, then this capacity is hit. And then even the reintroduction of contact tracing does not allow to recover the negative growth rate that we had originally. So basically we have, in this situation, we would lose control of an epidemic that would be controlled in presence of contact tracing, just because we have allowed the epidemic to grow too much. We have allowed the prevalence to rise too much. So I think a practical example in my mind is the very good summer we had last year, when the very low prevalence in all countries have, well, probably something else has contributed to this, but probably one of the reasons is the low prevalence allowed a very, allowed the contact tracing system to work at their best. To conclude, I just want to stress the strengths of the approach and the limitation of the approach. So why I like this modeling approach is that the individual processes are lifted to the population level to have a population description. So the advantage is that every term in the equation has a precise interpretation in terms of the individuals. So one can interpret quantities, one can go back and forth between individual parameters and the effect at the population level, like population level quantities. Then the since infection structure allowed to include realistic distributions of infectiousness, incubation period, or recovery time, and so on. And then the fact that the model is deterministic, although probably we lose a bit in terms of heterogeneity, but I mentioned this below. The fact that it is deterministic, it means that it is relatively easy and fast to simulate. So this may be convenient, particularly when simulation should be repeated many times, like in parameter estimation and model fitting. And it allows transparent relations and analytical formulas and relations between model parameters and output. Then I am very aware of some of the limitations of the model. The first one, which is very important in the context of contact tracing, is that we assume homogeneous mixing. This ignores clustering events or like structures like households or super spreading events like mass gatherings. And another limitation is, but that can easily be relaxed, is that the contact tracing here is assumed to be instantaneous, but this can be relaxed easily, including further delays. One other assumption we have is that infectiousness and incubation period are now assumed to be independent of each other, which is probably not very realistic. And then, yeah, now I presented forward contact tracing, but I'm confident that the extensions to backward and full tracing should be pretty easy and should follow the same approach. And what I also want to mention is that contact tracing, so the evaluation of contact tracing from a public health perspective really needs to assess the costs to individuals. And in this approach, we have only accounted for the tracing of infected individuals. We did not study the effect on the quarantine of healthy individuals, which could be included by adding further assumptions on the contacts that healthy individuals make with infected individuals. And this is all what I wanted to say. And if you have any question, I'm happy to answer. Thank you very much. And thank you again for the invitation.
Okay, thank you very much, Francesca, for a very interesting talk. And there is possibility to ask questions. You can either raise your hand. There is in the reaction, there is a possibility, and you can write on the chat. And, is there somebody who wants to ask a question? Okay. Oh, Marino, you can start, please.
Oh, okay. Thank you very much. Okay, very nice talk, Francesca. Now, if I do misunderstand your equations, you need anyway to know the prevalence of susceptibles at any time. Is that true?
Right. Right.
So
right, but unfortunately, I can describe the prevalence of the susceptible by using the incidence. So here I have an
so you
equation
update the prevalence.
Right.
Of susceptibles.
Yeah, exactly.
Sorry.
So I take out susceptibles okay. from the incidence.
That's the detail that I did miss.
Thank you.
No, thank you very much. Okay.
Yeah, thank you. I put it here because otherwise I must admit that the equation would not fit into a slide.
Okay, okay, great.
Thank you.
Okay, if there aren't other questions, I have a couple of questions. I start with one. You mentioned that you have when you show the simulation that there is a window of days that you follow. Where is it in the equation, this window that I missed?
Right. Okay, so I include that window. So, right, I include that window by setting the contact tracing rate at 0 after that window. And the reason is that if you, if I contacted, so if I was infected less than, let's say, 5 days ago, so if my age of infection is less than 5 days, if 5 days is the tracing window, then I have 0 probability of being traced because the public health system will never search for me. So what happens here is that basically after, so for tau greater than 5 or a certain threshold, this tracing rate would become 0. And this, so this could be the alternative way to introduce this in the equation is to make this epsilon time dependent or time since infection dependent, so that yeah, after 5 days, the number of contacts that are traced is effectively 0 because we are not searching for them.
Okay, so you basically in this equation, you're not really integrating from 0 to infinity.
No, that's even different. That's a very good point because I have several integrals here that go to infinity, but this is just for convenience of notation. That integral is made finite because I assume that the infectiousness is 0 after a certain time. So I imagine that individuals do recover at some point. So this beta will have compact support, so it will become 0 after a certain threshold, and this integral is finite. But the window is really due to the fact that individuals are not traced after if they are older than a certain age of infection. Yeah, that's a good point, a detail that I haven't mentioned.
Okay, other questions? And then, since I don't see other questions, I continue. And how do you implement a maximum capacity?
Right. Yeah, that's another good question. So I mentioned that I can compute explicitly. So having the solution at hand, or if I think in a numerical perspective, while I compute the solution, so while I approximate y and the calligraphic f, I can also compute the number of individuals that are diagnosed or traced at that time. So how I use this right now, I believe it can be improved, but how I use this is that I set a certain capacity here, and when this number of individuals that are traced hits that capacity, I somehow I make the contact tracing less effective. So I reduce this proportion epsilon of individuals that are traced of a quantity that is proportional to so how much the capacity is exceeded. Does this answer?
Okay, thank you.
Welcome.
Okay, I see another couple of questions. One is, well, since Marino asked, by Dream Big. I don't know who he is.
Hi, Francesca.
Hi.
I first of all, it was very informative, and currently I'm working on a similar project like this. So I think it would be very useful for me in my project as well. Thanks to you. Glad that I found your seminar today. And what I would like to understand here is that currently we're working on developing a risk model to understand how much does a person has a probability of getting an infection from an infector. So unlike the tracing that you're doing by understanding his contact with the person who is already infected, we are trying to incorporate parameters. So do you think the model that you have proposed today can have the capacity or the probability of incorporating parameters such as, unlike you have included age, we are doing air components such as CO2, temperature, humidity. What do you think about this? Do you think that that would lead us to finding a good risk model? We are still in the initial stages of it, so
Right.
yeah, I'm
So
trying to understand.
My instinctive reaction is that the model, so this approach is probably too little specific on the details of transmission, like air or surface, I guess you mean. So I think the best you can do with this type of model, to my understanding, is that you can kind of try to estimate the force of infection that you get from the environment, and then maybe you can link it to the infection prevalence in the population. But I honestly must admit that I've never worked with the risk assessment and with airborne and surface transmission. So I should, yeah, I'm not expert in this field, so I should think about it from scratch.
No problem.
But I'm happy to talk if you like, if you want to send me an email.
Sure.
Thank you.
Definitely, most definitely. Thank you.
Thank you.
There is another question by Marina, please.
Well, no, I wanted to know whether you need an assumption of stable age distribution to actually write down the renewal equations, and how do you, and whether you can in a way compute an effective reproduction number which varies in time.
Right. So I'm not 100% sure I get the first question, but well, maybe I answer the second question first, because that sounds easier. I think the effective reproduction number could be effectively computed by just scaling these formulas by the proportion of susceptible individuals. So probably if one has right, so basically by multiplying times the fraction s over n, I believe this should be enough.
Yes, it is what I have done too.
one question, so one.
I mean, that's the usual approach, that you multiply by the proportion of susceptible individuals.
I don't know if this is so probably this would need some work to justify theoretically, because one of the interesting thing that maybe connects to the first question when computing the reproduction number is that so to compute reproduction number, one needs to assume that the population is completely susceptible and then to linearize around the disease-free equilibrium. And what I found very interesting about this process is that, sorry, go back to the model. When I linearize the system, so this is non-linear in time. Sorry, non-linear in, well, this is a non-linear system in the variable. When I linearize around the steady state, around the disease-free equilibrium, I will get a linear, I will still get an equation for the tracing rate, which is now stationary. So has a stationary solution, in the sense a solution that is independent of the chronological time, but it's still a nonlinear equation. So why I think it may be related to your first question is because I don't need a stationary age distribution, never, but I will get some stationary profile of the contact tracing rate. Does this make sense?
Because, you know, usually when you write down the classical renewal equation, which is used by I would say by many research groups, Corey et al. 2013 or something like that. You need somehow to think that the system has gone to a sort of regime where the initial the memory of the initial conditions are kind of lost.
Right. So I think this. So I don't have demographic age here. So the age distribution in terms of demographic age is not here. But I think the same concept is for the shape of the rate in terms of the age since infection. I think that's exactly the idea. Is that
exactly.
Right.
It's the age of infection. It's like in the demography, but you replace the demographic age by the age of infection. And then usually you need to assume that you have reached a stable age distribution in demographic sense to write down the renewal equations, that the number of, say, the incidence at time t is the convolution of the incidence at time t minus tau time blah blah blah. Okay, but you need of course, if however that is close to the disease-free equilibrium, then we are now in a situation where we are somehow not very far away, but well, in some cases, very far away. So, well, I don't know. I'm not a mathematician, so I cannot solve the problem. So I wonder whether you have any idea.
Yeah, no, yeah, this is an interesting point. I believe this is related with the stationary form of the contact tracing rate, but there may be something else that I'm not thinking of. But yeah, that's what I was thinking, is that I should, when computing the effective reproduction number, maybe one should, I should be a bit more careful when I say that I just scale the reproduction number.
Okay. Thank you.
Thank you.
Okay, are there other questions? I don't see no hands. Well, then I think we can all thank Francesca for the very nice seminar, and thanks to you for being here and for paying attention. And I recall the next seminar will be in 2 weeks, and you can look at the page of the group to have information about activities. So have a nice afternoon and have a nice evening.